Okay, so I think what I'll do is I'll do very few introductory remarks while people are still filing in. I don't want to get too much behind schedule. Again, we're welcome to the first full meeting day for Quantum Noir. I thought we had a great tutorial session yesterday. I want to remind you guys, take pictures and post them. You can do quantum_noir at quantum_noir on Twitter. You can also tell Damon. Damon will also put them in other places. I kind of want to, I didn't mention this yesterday. I do want to kind of thank our sponsors, the National Science Foundation, who funded the vast majority of our gathering here, and actually our next gathering, which will be 2 years from now. National Society of Black Physicists, particularly grateful to the student chapter here between Harvard and MIT. The students have been fantastic in helping us roll along. Of course, the Harvard Physics Department and SEAS. The Harvard Physics Department, importantly, because the Harvard Physics Department never lets anybody use this room. And so, first of all, try not to eat anything in here. I don't want to get in trouble. But the idea that they let us use this room was a major concession for them because they keep this room like gold. It's fantastic. I also want to thank Bob Westervelt, the director of CNS, who's been a great cheerleader and champion through this whole process as we kind of walk through it. I'll show you the schedule today, but like I said, I think there'll be a poster of the schedule downstairs, and we'll have a few handouts around. I won't walk through kind of what we talked a little bit about yesterday, except I want to remind you that we want to take a conference picture just before lunch today. Actually, I should have changed that to today. We're still sorting out this issue with a job board, and I already mentioned to you about avoiding eating in this room. And so what I want to do first is I want to introduce our new dean, Professor David Parks, the George F. Colony Professor of Computer Science here at Harvard. He's also was the director of the Harvard Data Science Initiative, has extensive background in machine learning, AI, and computational machinery in general. He was named amazingly to be the Harvard John A. Paulson Dean of the School of Engineering and Applied Science. I'm not sure if that's a blessing or a curse. But he's gracious to actually come and gives us some welcoming remarks this morning. And so I'll step aside and give you David. Thank you.
Well, good morning, Bill. It's really great to be here. Let me add my welcome. Good morning. It's lovely to see you all here this morning. I'll let you in on a secret. I'm a computer scientist, but the physics department let me teach in this room. So you if you do things right, you can use this room. Welcome to Harvard, those of you that are not normally on our campus. I'm new to quantum science and engineering myself, but I will say that I've been learning and have already been seeing some remarkable things. And I remember the video that I saw of atoms doing computation back in December, and that was really remarkable to see. And hearing about advances around quantum networking as well. So before I get into my remarks, I also want to acknowledge Bob Westervelt here at the front for his leadership over the years at Harvard in nanoscience, leading the CNS. So over the next 3 days, you're going to hear from leading researchers in quantum science and engineering from Berkeley, Dartmouth, Harvard, Howard, MIT, Princeton, RPI, the universities of Maryland, South Florida, Texas, Washington, as well as the Oregon, Brookhaven, Oak Ridge National Labs. And I know that you already started off yesterday with some wonderful tutorials from Nashant and Julia and Neil. We have Bill Wilson to thank for this remarkable convening. It was his brainchild based on the simple premise that community building is central to progress and innovation. Bill was inspired by his positive experiences over the years participating in CARMS. Is that the right way to pronounce it, Bill? The Conference for African American Researchers in the Mathematical Sciences. And so he took it upon himself to create a similar community for the quantum field. He secured NSF support given his role as a member of the IBM HBCU Quantum Center Research Advisory Board. It was natural for him to reach out to include members from that effort as well. And Bill's vision was to create a community building event in quantum and nanoscience and engineering. And I was just hearing from Bill, I know many of you work in quantum, but don't often get the chance to get closer to the hardware. So it's really exciting that we've been able to, through Bill's work, bring you together. Graduate students, postdocs, junior faculties, leaders of the field, interacting with funders and entrepreneurs and VCs. Bill took his vision for Quantum Noir and made it a reality. That is one of the many reasons why he's such a highly respected member of our community, admired for his deep knowledge, his pragmatic can-do approach. So could I ask you all to join me in thanking Bill for his leadership? Quantum science and engineering is not for the faint of heart. Research in this field requires infrastructure and resources that are not readily accessible on many college campuses. And that's why advancing quantum is a team sport. It requires leadership from and collaboration between academia, industry, and government. And at Harvard, we have also a strong collaboration between the FAS and the Paulson School. And I'm also very grateful for the supporters of Harvard who have shared our vision and have helped us to take a leadership role. Advances in quantum science and engineering also require a broad and diverse talent pool, an area in which many areas of STEM have struggled over recent decades. And as you all know, this is not just a challenge in universities, it's a challenge through the talent pipeline. And to be competitive, we must change this. And that's why events like this are so important. This cause of building a broad and diverse talent pool was not helped by last year's Supreme Court decision on the Harvard affirmative action case. We will adhere scrupulously to the new standards that were set by that decision, and amid a national concerted anti-DEI campaign, we at Harvard remain committed to our long-term goals of broader inclusion and participation in science and engineering. As President Larry Bacow has said, I believe the talent is evenly distributed across society, even if opportunity is not. And I don't see any tension between our commitment to excellence and the pursuit of diversity and inclusion. On the contrary, attracting the best and the brightest requires that we build an environment that is inclusive. Building the quantum future also requires a multidisciplinary approach with the perspectives of quantum physicists, material scientists, photonics experts, computer scientists, and chemists, such as the Nobel laureate you will hear from, Mungi Bawandi, who will send his welcome and remarks in a minute. And lastly, I want to share that Harvard launched our PhD program in quantum science and engineering in 2018. For those of you that are undergraduates in the audience, if you're thinking about graduate school, please do consider applying to our program here at Harvard. It's literally across the street. And the new hub, the David E. and Stacy L. Goel Quantum Science and Engineering Building, is a dedicated space that will bring together the quantum community from across Harvard's campus and beyond, and it's actually opening officially this evening. Ideas will be tested there, experiments will be performed there, seminars will be held there, and collaboration will occur there. And I think more important than all of that, the next generation, we hope, will be inspired and will learn there. And I want everybody to feel welcome there. In the new Quantum Hub, we will collectively imagine and invent the future of quantum science and technology. So in closing, I applaud you all for participating in this inaugural Quantum Noir program. We certainly don't expect it to be the last. Encourage you to learn from each other, network, make professional and personal contacts, and help create the quantum future. There's no time to waste. Thank you.
I've actually known him since he was a summer student at Bell Laboratories in 1987, when I first started there as a staff member. His research group has focused on the interdisciplinary development of nanochemistry in a wide variety of applications, from biological sensors to the Q-dot displays you see used for televisions today. And all of that work, as part of all that work, he shared the Nobel Prize in Chemistry this past fall. And so I will get out of the way and I will start his remarks.
Well, welcome to this edition of Quantum Noir 2024. I hope it's the first of many. And I'm really delighted to be the first one in this series here to welcome you here to the incredible world of quantum mechanics and how quantum and nano sort of merge into each other, into this amazing world of opportunities and magic. So what I thought I would do, sort of to introduce myself and the field that I have helped sort of begin and expand over the last 3 decades, is give you the origin story of quantum dots and how quantum and quantum dots work together, and how curiosity-driven research from a long time ago, 30 years ago, unlocked a huge amount of opportunities in science and applications of these very small particles of semiconductors, which we call quantum dots. So let me start then by telling you a little bit about electrons in nanoboxes. So when we think of an electron, we think of a particle, usually that's is running around a circuit or a wire, and then we can follow it around. And in your computer, you think of electrons going from one processor to another processor, and etc. But when you take that electron and you try to stuff it in a really small box, a box that's on the nanometer scale, the properties that we usually think of the electron as being this particle, those disappear, and the electron now behaves as if it's a wave that fills the entire nano box. So we can't say where it is in the box, it just is there. And the properties that we need to think about then are wave properties. The nano box that we're talking about are the small particles that we create, the quantum dots. We call that quantum confinement. I call it magic, because it's so non-intuitive that you could take a little particle and that it behaves completely differently when you put it into the nano world. So when we talk about waves, the properties of waves are things that you already understand. It's like sound waves. You know that if you have a flute, the pitch of a flute is deeper than the pitch of a piccolo. That's because a flute is just bigger than the piccolo. And so if you put a sound wave in the flute, it'll allow a longer wavelength wave to be inside the flute than for a piccolo. And you can see the same thing then when you look at an organ pipe. So if you have an organ, it's got a bunch of pipes, got small pipes and big pipes, and you know that the pitch coming from the big pipes is much deeper than the pitch coming from the small pipes, which can be very shrill if it's very small. And this is the same idea. The waves that you can put in a big pipe, the wavelength is just longer than the wavelength that you put in a small pipe. So this idea that the box that you put a wave in for sound is the same as for electrons in a nanobox. So our nanobox, as I said, is a quantum dot. So what's a quantum dot? A quantum dot is a small particle of a semiconductor. It's got a few hundred atoms. The kind of semiconductor that we've been studying isn't silicon. Semiconductor comes in all sorts of flavors. The kind of semiconductors that my field studies are usually binary semiconductors that contain two elements. In this case here, cadmium and selenium are the two elements that gave birth to this field in a way. Cadmium selenide is the semiconductor. And it's nanometer size. It's on the order of a few nanometers, maybe 2 to 10 nanometers. And so a quantum dot is simply a nanometer-sized particle of a semiconductor whose electrons show these quantum effects, these quantum size effects. Now, something that's nanometers, you can't see with a microscope because a microscope is limited by the wavelength of light. The wavelength of light is many hundreds of nanometers. This is so much smaller than the wavelength of light that you need to go to an electron microscope where you shoot electrons that also then become waves, just like light is a wave. And we can then image nanometer-sized particles, electron waves that are very small, that are on the order of nanometers. This is one of my students from many years ago, sitting on an electron microscope imaging these quantum dots. And when you do that, you see these images that are like this. And this shows an image of little particles that are each probably about 4 or 5 nanometers in size. And if you make them all the same, you have the quantum boxes that are basically all identical. And then you can start to do some science. You can start to do science and then think about what could they be good for. So these electron in a nanobox requires wave properties. And the size of the wave, as in the flute or the organ pipe, determines something about the electron. Okay? For the electron, it's not the pitch, but it's the energy of that electron in there. The small particles or a small wave will have higher energy than a large wave. How do we put an electron in these nanoboxes? They're already full of electrons, but all the electrons in there are tied up to the atoms that make up the box. They're next to cadmium, they're next to selenium. They're not free to be free in the box. The way that we liberate an electron from an atom is to shine light. We can shine, let's say, blue light and excite that electron from the atom that it's bound to and let it occupy the entire box. So that's how we put an electron in the box. I mean, we could also try to put a wire and put an electron in there, but this is a lot easier. We usually use blue or UV light and just excite it, like you would pluck a guitar string to create a wave or blow in the flute to create the sound wave. Here we use the blue light to generate the electron, this excited electron. Eventually, that electron wants to go back to the atom where it came from. And when it does that, it releases the energy that's in that wave. So in a small particle, where the wave is small, the energy that it releases will be bigger than the energy that it releases from a large particle. And the energy is released in the form of light, also another wave. And for light, we know that high energy light, like blue light, has a smaller wave than low energy light, like red light. And so everything ends up being this magical property of waves. And that's where we see then fluorescence coming out of the particle. So these vials are quantum dots of different sizes in an organic solvent. The green ones are smaller, the red ones are bigger. We're using blue light to liberate the electron. Eventually, the electron fills the hole that's it left behind, or it finds the atom that it used to be next to, and the energy is released. Small particles have higher energy light coming out. Big particles have lower energy light coming out. That's what a quantum dot is. So now let me tell you about the origin story of the discovery and synthesis of these dots. So the discovery of and synthesis of the dots was rewarded by a Nobel Prize in 2023, and I was lucky enough to be part of the trio of that Nobel Prize. There are 3 of us, Louis Bruce, Alexei Yakimov, and myself. Louis and Alexei were part of the discovery. Let me tell you a little bit about that. So this is how curiosity sometimes leads to amazing things. So Alexei Yakimov, he was interested in understanding why colored glass in stained glass in churches or cathedrals, why they had these beautiful colors. It was already known that the red color came from very small particles of gold. When you take gold and you break it up into tiny pieces, it doesn't look like gold anymore. It looks red. And the other colors, the recipes, talked about adding all these metals and other heavier elements and all sorts of things in there. And so he decided to try to get rid of everything except the few elements that he thought were important to create the color. And so he put it in glass and started melting the glass and heating it up and cooling it down in different ways. And he found that with only glass and a couple elements to form a semiconductor, a binary semiconductor, a semiconductor that contains two elements like cadmium selenide, depending on how he processed the glass, he would get a different color. And so he was wondering, why is that? And because he was surrounded by physicists that were thinking about quantum in very deep ways at the time, he realized that what he was observing was quantum magic. He was observing those electrons becoming waves in the semiconductor, and the size of the box then gave rise to the color. And he wrote a paper about it. Louis Bruce, so Alexei Yakimov was working in Soviet Union. This was in 1981, 1982. Before the fall of the wall, before the fall of the Berlin Wall, and he was very isolated from the West. So there was no connection between the research that he was doing and the research that was being done in the U.S. Louis Bruce, around the same time, was thinking about how to make renewable fuels from sunlight. And one of the ideas was that you could take a semiconductor, capture the sunlight in the semiconductor into electrical energy, and have those electrical energy, those electrons that you create from sunlight, excited electrons, to capture those in solution to do chemistry. This is basically photochemistry, to create fuels that way. And he was interested in understanding the dynamics, the kinetics of how fast an electron can go from inside the semiconductor through the surface into the solution to do the chemistry. In order to get better signal to noise, he thought he should get smaller and smaller particles to increase the surface to volume area. And he found that the particles that he was making, which were nanometer size, as he let them sit on the shelf, the color changed again. And he realized, using an electron microscope, he was able to correlate then the color that he was seeing with the size of the particle. And because he was working at Bell Labs, again, surrounded by physicists thinking deep thoughts about quantum mechanics, he realized that this was the quantum size effect. And so Alexei Yakimov and Louis Bruce discovered the same effect, essentially simultaneously, one in the Soviet Union and one in Bell Labs in the US. And that's the discovery part. Where do I come in? Well, I was a postdoc with Louis in the late 1980s. And the particles that we were working with were not particularly good in the sense that they were not crystalline, they were misshapen, they were made in water. And these semiconductors really actually don't like water very much. They oxidize. And so instead of having, say, cadmium selenide after a little bit in the presence of water, you'd have cadmium oxide, not exactly what you want to study. And so I had discovered a way to make the particles a little bit better at Bell Labs by transferring them from a water-based synthesis to something that had organic solvents, and then heating them up to try to get them a little bit more crystalline. When I came to MIT, I proposed to have a very fundamental science project where I was proposing to try to understand how bulk properties emerge from the properties of atoms. You know, an atom has properties that are completely different than the properties of the solid that it eventually makes up. The atoms make up the solid. So there's this transition that happens. And me and as well as others in the field, this very small field at the time, we're interested in understanding this transition process. You have the atom on one end, you've got the bulk properties on the other end. What happens in the middle? And I needed samples. And I tried to reproduce some of the stuff I had done at Bell Labs, and it just didn't work. It just didn't work. So I was very, very anxious at the beginning. But I had two great graduate students, Christopher Murray and David Norris, who I told, you've got to make these samples because otherwise we're screwed, pretty much. Well, Chris Murray took me up on it, and working with David Norris, who was eager to do some physics experiments, we developed what is now called the hot injection synthesis of quantum dots. And in retrospect, it's a pretty simple idea. So instead of using a water-based synthesis, since water was such a terrible thing for semiconductors, we replaced the water with organic solvents. We got rid of air because oxygen also was a terrible thing. So everything was done air-free under nitrogen with organic solvents. We used what are called organometallic precursors to bring in the metal atoms that make up the semiconductors, metal organic precursors that are under nitrogen, that are stable at room temperature. And the idea was an old idea to do nucleation and growth, but at the nanoscale. Nucleation growth is something that you already understand from snow, from snowflakes. You know that if it's a dry day, cold, dry day, that the little seeds of ice that form in the clouds, when they come down to become snow, they stay really small. And they're all really small by the time they get to the bottom. It's because there's not enough water in the air to aggregate more for those snowflakes to grow. But if it's a warm, humid day, there's a lot of water in the atmosphere. You form the same little seeds in the clouds, tiny little seeds. Then they come down through the atmosphere and they begin to aggregate water molecules, and they get bigger and bigger and bigger. They nucleate in the cloud and they grow as they reach the ground. And then you get these big, fluffy snowflakes that are all basically the same size. So if you can engineer nucleation and growth properly at the nanoscale, you should be able to get the same sort of size control as you might have with snowflakes. That was the basic idea. And so we developed this process by which we inject very quickly these metal organic precursors in a hot solvent. They reach the hot solvent, they decompose, and they begin to react to form these little seeds. The temperature goes down, the concentration of the precursors goes down, and the seeds stop forming. It's basically like the little seeds of snow leaving the clouds, entering the atmosphere. And now we have growth. We can control that growth slowly and stop the reaction whenever we have the size that we want. So I'll show you a little video of what that looks like. So this is a video of this hot injection for making quantum dots. And you'll see then the quantum magic with your own eyes as the color changes, as the particles get bigger. So let's see what happens here. And he's going to do the injection into the hot solvent. Taking the cover off the syringe, and you see this flask that's at 350 degrees Celsius. Quick injection, precursors grow, and you see an immediate color change. Those are the little seeds of cat selenide. They're about 2 or 3 nanometers in size that form. He's taking samples out to show us what's happening as the particles then grow in there. And I'll spare you the 20 minutes of growth. And here now it's much deeper color, so the particles are bigger. The wavelength of the electrons is larger in these particles. Then you can see the series of color changing. And when you shine a UV light on these particles, then you can see that electron, then that excited electron returning to the atom from which it came and emitting these photons of different energies, of different wavelengths from green to red. So that's the origin story. And that was in 1993. Let me go ahead and stop this. And since then, once we had samples that were all the same size, that were really well defined, which was really the key to begin to understand the science, applications came out. Because when you have a new material with new properties, and you start asking the question, what is it good for? Turns out that usually you find reasons to use it for something. And today, the main application is in displays. If you have a television or display monitor made by Samsung or some of the other companies, it's very likely that it has quantum dots in it where the color, the red and the green color, is created by exciting electrons and letting them relax and emitting green and red light. And the blue light comes from another discovery from the 1990s, which are these blue gallium nitride LEDs. Science is amazing. It gives rise to technologies that change the way that we live. And this quantum thing is really beautiful, really magical. And so there's so many opportunities. So I wish you a great conference and a great journey into learning more about quantum and nano-sized materials.
And so I'll introduce our first speaker, James Whitfield. Professor James Whitfield is from Dartmouth College. He's an associate professor of physics at Dartmouth College. But as we were saying yesterday, James, like me, started out as a chemist. He did his bachelor's degree in chemistry and mathematics at Morehouse, did a PhD in chemical physics here at Harvard, and has since been a faculty member at Dartmouth, but he's also been kind of a visiting scientist, and I think he'll tell you a little bit more about his role in the quantum computing activity within Amazon. And so he's kind of had one foot in the Amazon door and one foot in the Dartmouth door. And I think he'll walk us through a little bit of that history.
All right. How exciting. How exciting. I was here last fall to give a talk about my research for the quantum technology seminars. And that was wearing my Dartmouth hat. Today I'm here as an Amazonian. As you can see, I'm both Amazon visiting academic as well as a professor of physics at Dartmouth College. I actually got my PhD here in chemical physics with with Ilana Spru-Guzik, and it was great. In fact, some of my teachers are in the class, are in the audience. Right now, I'm a professor of physics at Dartmouth College. Okay, we heard the advertisement about the graduate program at Harvard. Don't forget to apply to Dartmouth. My research group is relatively small. We have a few other professors who are doing various types of quantum computing, quantum technology, theory, and the like. We have about 100 people in our graduate program, and my research is sponsored by NSF and the Department of Energy. And as I said today, I'm not really going to talk much about my own research. I'm going to talk mostly about the Amazonian things. But let me first highlight my group members. So Weishar is on the left, followed by Jason, who's an MIT alum. We have a lot of MIT's folks here. Myself in the middle, Andrew Prjansky. We have Casey Dowell and Brent Harrison. We do a lot of mathematical physics related to quantum computing. Okay. So my role at Amazon is a visiting academic, and I think it's been very interesting. You know, I didn't start working, I've never worked anywhere but in an academic setting until I took this part-time position at AWS. And it's been very interesting to see the differences between the two sides of what are possibilities. I know this conference has a lot of people who are thinking about what their next steps inside their career are, thinking about where they're going inside of what they can do. And so one of the things I'd like to highlight at the beginning is just some words about what the differences are. And so for me, as an academic, I think most of you guys in the room will have a good idea. It's a lot of things around mentorship, around intellectual discoveries, around making things that make you feel intellectually satisfied, as we just heard from the last speaker. On the other hand, when we talk about being in a company, in particular for Amazon, there's a huge emphasis on customer obsession, where it's really all about things that have a business purpose, things that have a product that can be produced for a customer need, for customer interest. You don't do things just for fun. You do things because customers are asking for it. And so what I'm going to talk about today is what are some of the motivations and what are some of the things that AWS have done inside of the space. But because this is the first talk, I did not attend the tutorials yesterday, which I heard were very good. I will start off with some motivation of quantum. I think it's very interesting that we just heard this analogy of quantum through the instruments, because that's also how I thought about this as well. So maybe just to bring in the same ideas that we just heard yet again, we have this idea of music giving rise to quantization. And so I picked a trumpet instead of an organ, but the idea is still the same. Whatever the boundary conditions are of that instrument is what's determining the fundamental mode, the first, second, and these are all called overtones inside of music, and inside of quantum, these are the quantized levels. So quantization is something that happens and you count by discrete integers versus something that's continuous and uncountably infinite. So that's all the numbers between 0 and 1. You have an infinite number of numbers, but it's in a very small domain. So you can think about this being very distinct from what happens in quantum mechanics, where you have integer spacing between whatever items they are. Okay, so the next thing I'd like to motivate to step a bit further into quantum is quantum information. And so quantum information I like to motivate with the story of Maxwell's demon. So Maxwell's demon is a fantastic thought experiment that really gets everyone back into their thermodynamics and thinking about how information connects back to this notion of disorder. And so here's a quote from James Clerk Maxwell from his 1867 book, The Theory of Heat. A being who can see the individual molecules open and close these holes, so as without expenditure of work, raise the temperature of B and lower that of A in contradiction to the second law of thermodynamics. So for those of you who do not know the second law of thermodynamics, the easy way to think about it is that heat flows from hot to cold, and not the other way. And here, there's a little tiny demon who can open and close a door, and he can let hot particles go to one side and sort them. And as he sorts these particles, he lowers the temperature and creates a temperature gradient that's opposite what the second law of thermodynamics tells us. So in thinking through this resolution of how do we protect the second law of thermodynamics, protected, of course, is a statistical argument. So you can make lots of different arguments against Maxwell's demon, but it's just a thought experiment. And one of the early pushes into this thought experiment is Slizard's, I think it's Slizard, I'm not sure how to say it, Szilard engine. So this was an American-Hungarian mathematician who was very instrumental in getting the nuclear weapons program off the ground in the between the world wars. So here he simplifies this model and says, well, the Maxwell demon's a little complicated. Think about a bunch of gas particles moving left and right. So I'm going to take everything away, get it down to the simplest case, as we just saw inside the Nobel Prize discussion. Go into the simplest cases where you want to start. And here you can't get any simpler of a gas model than just one particle. So you have this one particle, and this demon's at the top, and the demon will look on which side of the particle it is. Particle's on the left side or the right side. And what he's going to do is extract work based on which side it's on. He's going to put a partition in the middle, and that partition will then do work. So here's an illustration. So he put in the partition, he saw that the particle is on the left-hand side, puts in the partition, and waits for that particle to push the wall over. As it pushes the wall over, you extract some work. This little red object moves up a little bit, and then you put it in, you set it up again, put in the partition, it goes up a little bit. And this way you can extract work from the setup by putting the pulley either on the left or the right, depending on where the particle is. If you are quick on your feet about thermodynamics, then you can work out what the work done is. It's actually KT log 2. Okay, log 2. Those of you who want a quick reminder, refresher, PV equals nRT. RT is KT for single particles. And you just take the log of this, and you have 1 over double volume over single volume, and then you have log 2. Okay. Didn't make sense, don't worry. If you know this from thermodynamics, also from the point of view of information theory, if you erase one bit of information, it costs you KT log 2. And so this idea of the thermodynamics, the entropy that the demon's memory is accumulating, matches the amount of entropy that the demon's able to lower inside the situation. And so this is one arguable resolution to Maxwell's demon problem. And the crux of this is that information itself is physical. And here you see an equivalence that you can argue for or against, but here we'll take it as given, of an equivalence between information theoretic entropy and thermodynamic entropy. And that really goes to the core of this idea of information being physical. If we take this idea of information being physical, we can start to think about things like quantum computing. And so in fact, some of the early ideas around quantum computing were founded by people thinking about what is information, what is the physics of information, and then that leads you into thinking about information as something that could be quantum. So information as being physical goes back to the beginning of humans' recorded history. In fact, recording history requires us to write it down somewhere. We pass markers, rocks, stones to indicate things to one another. Then we advance. We can use cuneiforms. We can leave marks inside of clay, start to set up languages. But again, you can see that the information is being stored physically inside these marks that are in the clay. We go on to abacus, another physical device where we move things up and down to help us count and calculate. And then finally, we get the clockworks, gears, and very complicated setups that are also allowing us to process and store information. So this idea of information being physical continues on, where we talk about vacuum tubes inside the ENIAC. We talk about semiconductors being developed, again, at Bell Labs. We have integrated circuits. And then finally, we come to the atom itself. So as we miniaturize devices smaller and smaller and smaller, we can only get so small till we're down to one or a few atoms. When we're down to one or a few atoms, the rules of physics dictate that we should be using quantum mechanics, either fighting quantum mechanics or using quantum mechanics. So if we use quantum mechanics, that's where we get to ideas like quantum computing. So when I teach quantum computing, which I just finished a course on quantum computing, the way that I like to motivate and think about quantum information is thinking first about probability. So thinking about probability first helps us think about what are we actually looking at. And so on the left-hand side here, you'll see what's called the Bernoulli line. This is if you have Bernoulli trials, you flip a coin, but that coin happens to be biased. We can represent how biased it is by a vector pointing towards the outcome 0 or pointing towards the outcome 1. And so as it's pointed all the way towards outcome 0, every time you flip the coin, it just lands heads. And if it's pointed all the way at the bottom towards outcome 1, every time you flip the coin, it comes out tails, and then something in between. So this notion of a bias vector, you can generalize to reach the Bloch sphere. And I think starting from the bias vector of ordinary probability gives a much more fulfilling thought about what your understanding of the qubit state as a Bloch sphere. So we measure the quantum state of the Bloch sphere. If it has unit length, then we're at the surface of the sphere, and then that means there's some direction that we have a deterministic answer. If we want to think about probability, coming back into quantum mechanics, then that vector would not be unit length unless we know that there's some direction that we have a definite outcome. And so really thinking about this notion of the Bernoulli line gives us a way to think about measurement inside of quantum settings and a way to think about how we're generalizing from quantum to classical, or from classical to quantum. This was a subject of a blog post that I wrote with one of my former students. Shout out to QBraid in the audience. In any case. The main notion that we want to do when thinking about quantum computing is the difference between using digital bits and quantum bits. We have quantum bits. We allow for things like superposition. We allow for things like entanglement, which is beyond classical correlations. And these two ideas help us think about what resources we can use from quantum to make technology. It's really at the crux of what we want to do. So potential applications come inside of many different areas that people talk of using quantum technology. I mean, many of these applications are around optimization. Many of these applications are around applications to finance, to pharmacy, to energy, to logistics, all sorts of problems that can show up. And at a company like AWS, the idea is to enable customers to figure out what's going to work well for them. And what we're going to talk about now for the rest of the talk is how delivering this quantum technology goes. So when we think about delivering quantum technology, I'm going to give a very broad introduction to what needs to happen to deliver quantum technology to a customer or to a person who wants to use a quantum device. And so this is quite a high-level case here. And what I'll talk about is what are the solutions that AWS has built to answer those problems. So if we think about delivering quantum technology, there's three things that I think every delivery quantum technology needs. One, you need access to the quantum technology, quantum device. You need algorithmic support to actually run some algorithms, to run some problems on that device, figure out how you interface with that device to get out interesting answers. And finally, thinking about assessing the cost, the value. So I think assessing the value is a very interesting concept because a lot of the work inside of quantum computing for many years was just around theoretical promises, around what the promised fidelity is, what the depth of the circuit is. But now we can think about, instead of just depth and fidelity, think about things like actual cost to solution. And so when you think about actual practical applications of quantum of computing in general, the cost of solution is an important factor to consider. One of the major ideas around accessing quantum computers is that it will be accessed through the cloud. And so thinking about cloud access, this is where AWS is really a company that really stands out. This is a company that does nothing but cloud computing. Well, not nothing but cloud computing. It does cloud computing. And what cloud computing is delivery of digital resources through the internet. So the idea is that AWS maintains all the hardware, updated, fully vetted, all the way through the physical security, and then you build your applications on top of AWS. The web services are just APIs that allow you to access technology remotely. This is on-demand, pay-as-you-go delivery, with the idea being that instead of buying a server, provisioning a server for your website, you buy, you set up a server virtually, and then as you have more customers show up, you don't buy another hard drive or another server. You just let it auto-scale, and you just pay for what you use. Okay, and there's over 200 different services that are across the AWS ecosystem. So anytime you go to a website and you click and it downloads and you read AWS S3, blah, 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 inside the PDF download of the menu, they're using AWS Web Services for the website. All this to say is that Amazon Braket, which is the AWS quantum computing service, is the way that we deliver this to customers as part of the existing AWS ecosystem. So Amazon Braket is a fully managed quantum computing service that allows customers to get up to speed and test out quantum devices as part of the entire AWS Amazon Web Services setup. Okay, so architecture diagrams for anybody who's actually into web development. Okay. So if you actually use AWS Web Services, this will make a lot of sense. If you don't, I'll walk you through this briefly. So do I have a mouse? Do I have a pointer? Oh, you can. Okay, great. Okay, so we have these 3 different ways to access it. You can access it, you just write your code inside of several different choice of languages. Then it gets sent to, I cannot see my mouse. It gets sent to the AWS cloud. From the cloud, it connects to either a managed simulator or to one of the third-party devices that are available. I'll talk about these 4 different devices in a moment. And then alongside that, on the right-hand side, what you'll see is a list of different services that AWS offers. These are all industrial level services that work with the highest level securities for things like governments all the way through to academic institutions. So this is to manage permissions, store the results, to get notifications when the results are running, so on and so forth. Anything to do with cloud computing would all be available to you as part of this AWS system, including the service and security promises thereof. So with Amazon Braket being a fully managed service, we also want to make it something that is useful for both customers as vendors and customers as users. And so the idea is to connect these devices that are available to users who want to use them. There are 4 different devices that are currently available. Varying over different types of quantum devices. So as we go throughout this week, we'll hear about different types of quantum computers, ion trap-based quantum computers. We have superconducting quantum computers and trapped ions. So QERA, founded out of Harvard here. IQM in Europe, Rigetti, and IonQ, also American companies. So these QPUs are all available, and the next thing that we need is, so now we talked about accessing these devices from the cloud. Almost all the quantum computing paradigms that people are building are all through cloud access. There's other ways to cloud access devices. These aren't the only 4 devices available. However, the idea of accessing devices is all through cloud networking, rather than building multiple devices for each user. Okay, so for algorithmic tools, in order to actually use this device, you still need a variety of different things. You need to build whatever task you're going to do, test it, and then you need to run it against the device to learn what's going to happen. And so when we say build, you construct some quantum circuit that maybe has, here we're just doing some phase estimation type circuit. And then you run it, you send it off to the cloud, and the cloud runs it over some device, multiple instances, and it comes back with some answers from the QPU. And then you're going to run it where you're going to have some interfacing between the QPU and the CPU. If you're doing something like optimization, where you get some feedback from the quantum computer, update the parameters in the classical computer, and go back. So all these ideas in AWS, we call one run of the task, one run of measurement, a shot. And then the task being how many shots and what the instructions are. And then you pay a per task fee and a per shot fee. And then as you run the job, we also have a feature called hybrid jobs that allow you to lock in the classical and quantum resources and go back and forth. So that way it's more tightly coupled running of the system. Yeah. Now, just like I said, there's a diversity of tools, diversity of devices you can use. There's also diversity of application tools, development tools that we have. So the Amazon Brocket SDK is available on GitHub. You can pip install Amazon Brocket. But in addition to just Brocket, we have several different other APIs that also work well with Amazon Brocket. So Penny Lane, QBraid, who you'll hear about later this week, QuizKit, which is IBM's solution. Brocket JL is a Julia language library. If anyone uses Julia, which is a very popular or up-and-coming popular language to replace Python, also very cool code. All the rest of the code, all these other packages are in Python except for the Julia package. So all these packages you can code in whatever language you want and then run against the devices on AWS. And then just to say something about assessing value. So I think when we talk about quantum computing, you talk about quantum computing in a vacuum, talk about quantum computing in light of the generative AI ongoing phenomenon in society. There's a lot of questions around what are we spending money on. There's a lot of issues that are coming up in society around where we're spending our money. And so assessing value for how much we're getting out of quantum computing for how much we put in is also a very important component of thinking about the future of quantum computing. So with Brocket being a fully managed service, you get all the other things that allow you to understand what the cost is. So first, if you just use the quantum device, you can use it in two modes where you pay for cost and you pay per shot, pay per task and per shot of the task. So you might pay 10 cents for the task and then 1 cent for every shot that you want to do thereafter. Then you can also do time-based. So there's also a reservation system that if you want to reserve a quantum device for a certain amount of time, then you can reserve it. And then there's reservation-based cost through Brocket Direct. Because it's a fully fledged AWS service, it works with all the other management tools for cost. So if you're an AWS engineer, you'd already be familiar with a lot of these ideas. And then lastly, we just released Amazon Brocket most recently. And this is a reservation mainly for corporate customers that might want to reserve a device for some fixed amount of time to run some experiments. Okay. And so now what I'm going to turn towards is just a few applications and a few other things with quantum computing. So as I mentioned, AWS being a large set of services means that you can run full workloads with it. So Good Chemistry is a startup company that was recently purchased. However, what they built was a chemist package that allows you to run quantum chemistry on demand. It's run on AWS, both classically and quantum mechanically, and this is some work that they built, the Chemist Cloud. And so you can see that this allows you to interface with the entire AWS. Again, another systems diagram here. And here's a quote from our customer that they are able to run spot instances 1.1 million CPU cores. And so they were looking at several different molecules, and they were able to come up with some really nice cloud-based classical computing quantum chemistry services that also allow you to integrate quantum services therewith. And so when we think about where quantum computing will play a role inside of quantum chemistry, what better way to think about it than thinking about an integrated solution where you already have something that's deployed to give you answers inside of quantum chemistry, and you can ask for quantum resources to improve those answers, to improve the time to the solution, or whatever it may be as the quantum devices get more powerful, as they become more performant. Okay, And so now with the last 15 or 10 or 15 minutes, I want to talk a bit about what else AWS is doing in quantum technology. And so I'm going to talk about a few other things that we're doing at AWS besides Amazon Braket. And first, let me say, why are we looking at quantum technology at AWS? So AWS, as I mentioned earlier, is customer-driven. Almost everything that we do is driven by some customer demand. A lot of people are interested in what quantum computing can do for their particular business application, for their particular scientific deployment, whatever it may be the case, whatever innovation they're trying to pursue. At AWS, across the board, we're thinking about all different ways we can facilitate that improvement and help learn with our customers. And in particular, quantum is one of those areas where we can learn about what's going on inside the industry, help customers learn about what's going on inside the industry, and connect them on both sides of that conversation. So that's really what the idea is, to envision how quantum computing will be integrated into IT infrastructure writ large, rather than it just being a standalone technology. So at AWS, there's 4 pillars. We've talked about Amazon Braket, which is the quantum computing service that connects you from your device to quantum vendors. There's also the Quantum Solutions Lab, that if you need expert guidance or someone to spec out an entire problem for you, there's a number of top-level scientists who are there to provide cross-discipline support, where they'll solve it either using quantum or classical solutions, depending on what the best approach is. Those are paid engagements. The Center for Quantum Computing is based out of Caltech, and their mission is to build a fault-tolerant quantum device, thinking through error correction and quantum algorithms. The Center for Quantum Networking is pushing the boundaries, especially here in Cambridge, thinking about how do we set up quantum communication networks. And I'll walk through a few examples of each of these. So first, for the Quantum Solutions Lab, with JP Morgan Chase and AWS, they've used this QERA device with these neutral atom arrays to think about what sort of problems would be of interest for financial securities, what sort of problems would be of interest for quantum computing at all. And so what they did was look at this problem called maximum independent set. So each one of these gray dots represents a node of a graph. And in that graph, you are connected to your nearest neighbor if you're within a unit disk, this yellow unit disk. So everything within one yellow unit disk of each other is connected. And so you see all of the dots within that yellow disk connected to the central dot. And if you do that for every single dot, then you produce the graph on the left. On the right, finding the maximum independent set is finding the set of nodes that are not connected and that form an independent set. So in formulating this problem, this is an optimization problem. It's a known NP-hard problem. You can encode other problems into this. And so the question that they were investigating is, what interesting problems can we put in here? What are the challenging problems for quantum computing? And what can we see that we can do with these quantum devices that we couldn't do otherwise? So that was over the past year. And this is published on our quantum blog. And it was a collaboration illustrating some of the problems that we can solve with this Rydberg array. The Center for Quantum Computing, as I mentioned, is based out of Caltech. This is a research and development center that's focused on building fulfilling the long-term, large-scale vision of building fault-tolerant quantum computing processors. These quantum QPUs are all superconducting-based, and the architecture is still being developed, right? And they do original research on the quantum algorithms and the hardware, thinking about both near-term applications as well as how to build error correction inside of these devices. Okay, and then coming up on the last few comments here, the Center for Quantum Networking is thinking about how do we actually set up quantum secure links. So a lot of the efforts inside of quantum technology have been around security, around making sure that you can have secure links. I think during the South African World Cup, they had used quantum links for some security reasons. And what we've done was think about how to actually deploy that. This one's, I think, really appropriate to talk about here. This was done actually at Cambridge. So in the insert, you'll see this is just about where we're at here. And this is just swapping quantum information from one side to the other over a field-deployed quantum network. And these are silicon vacancies inside of nitrogen. Okay, and with that, I want to come to the conclusions, just to talk a little bit about what some of the things you can do to learn more if you're interested. In particular, if you're interested in latest quantum developments, at least from the AWS perspective, the quantum blog, Quantum Technologies blog, is where we release a lot of information about the latest service updates, the latest customer engagements, and the latest things that we have of interest to offer to our customers. If you're interested in programming, coding, contributing, or getting involved, the AWS on Brocket on GitHub, the GitHub organization has several different repositories with tutorials, with algorithm implementations, with labs, and similar ideas there. And then the digital badge, I will promote that one personally because I was one of the owners of creating that. So if you want to know how AWS works, at least to get started, you can get a free digital badge. You just go through, click through, and you'll have at least something to say, hey, I at least know the basics of how AWS works, how AWS Quantum works, and what are some of the things you can do with that service. And that's the main idea. I'm James Whitfield again. Feel free to reach out if you have any questions, academic or industrial, and I'm happy to take questions now. Please.
All right, so thanks for a fun talk. So there's a lot of toys that I've seen, right, for quantum, right? Like even in my own field of neutron scattering, somebody will go and say, okay, I can calculate SFQ and omega, but for like a singlet triplet excitation, something you could do analytically.
Sure.
And your customers, I'm imagining, have a similar thing where with existing technology, you can play with some toys. How big do systems need to get to the point where they're interested for someone like JP Morgan or someone else to actually use? Like how many qubits are we talking?
That's a great question.
Or magnitude or
Yeah, at some level, it's a guess. I would say that one of the interesting things that's been going on in the literature over the last couple of years is actually making that argument about what is the requirement. I think a lot of people have made that argument about what the requirements are, where you say, hey, I have this experiment that you can't do classically. I'm going to build my device and I'm going to run it, and then I'm going to ask you, can you match? And what happens is that normally someone comes out with some claim, and then maybe a month or two later, people just figure out how to set up their classical devices to run faster, to run better, smarter algorithms, exploit symmetries to then reproduce the result. And it's been happening quite a bit. There's, I think, maybe only one, maybe two standing quantum primacy results. And so right now, it's really early stages, and even answering that question of how many qubits do we need to say that we can at least do something that we can't do classically is still out for debate.
Hey, James Bertone. I'm a fifth-year chemistry PhD student at Yale. You were mentioning before about how you see, this is unrelated to qubits, sorry, but you seeing Julia as being the next Python. I wanted to ask you why you thought that.
All right, so, okay. Great question. I will say for Julia, all right, I've used Julia, I use Python. Python's a little bit easier than Julia, but Julia is much, much faster. If you want Julia to run well, you can get it to run very quickly. Julia runs close to Fortran speeds without compilation. You have to be careful about how you construct the code. However, if you write Julia correctly, you can get it to run very quickly. The first time it runs a little slow, compiling once, and then it runs much faster. So a lot of people have it as an eye for replacement for Python. Second reason why it's a useful idea, at least to consider as a replacement for Python, is that most Python you can run in Julia, maybe not quite the other way around. So if you wrote everything in Python, you can still import a Python package to run in Julia. However, it will, of course, slow down your entire setup. But if you write Julia correctly, you can run at Fortran speeds without going through the full effort of compiling. It's my short Julia avid.
This is Denmark Elisma from Howard University. It seems that a lot of companies are in the business of creating the hardware, hoping the customer will find a solution of how to use their hardware. Is that the same model that Amazon follow, or do you have a pretty fine set of problems that you use on some platform, or you take the platform and solve the problem?
Great, thank you for the question. So I'll say that for the devices, just writ large, I think they're all being built without knowing exactly what the precise goal is. I mean, not to say not at all. There's a lot of ideas like factoring, but what's the short-term goal? I think is kind of up for debate. At AWS, in particular, the way that we answer that question is customer first, right? So if customers stop caring about the applications, then so would we. I think the customer being interested, the customers building these devices, customers interested in using the devices is exactly why we're in that space. And so for us, it's all driven by customer demand. And I think the question of what will it do for you, I think this is exactly why it's part of the full infrastructure, that you can think about how this will work if you were to deploy it, versus just doing a one-off experiment to show that quantum devices work, or doing a two-off experiment to show that you have high gate fidelities. How do we get this to give us better answers for, traffic allocation, for instance?
Hello, Alejandro Ponte here. You have a pretty unique insight because you're probably one of the few faculty who is also extremely involved in industry. And typically when you talk about quantum computing, you either have to choose, you want to go the academic route or the industry route. And you've kind of created a path for yourself where you're able to follow both. How can you, or can you speak on your experience and the differences of having to do industry versus having to fund your own research and find, like you said, you were funded by NSF, having to find funding for it versus already having the funding for it and being able to do it, but it's more driven on a customer basis and what the needs of the market are, as opposed to your own whims?
Yeah, I think that's true. I think there's, at least, I'm not sure what your level is, but I know from my own graduate students, talking to them about what it's like to be in industry versus what it's like to remain in academy. A lot of people have either a rosy-colored picture of industry or like whatever the opposite of rosy-colored is, darkly colored. And I think that, industry is a very wide thing, and to think of it monolithically, I think is the wrong way to think about it. If you go into industry, right, you can go in a lot of different levels. If you're in the academy, you're an academic. There's not really a lot of different distinctions. There's not like a document writer for courses. There's not a textbook writer for this. There's not a legal approver for that. Whereas if you go into corporate, you can be on the quantum team and not do any quantum. You could just write the documentation. You could interface with customers and help them go from where they need to go to where they need to be. And so there's a lot of different things inside of industry that are very different than just doing research. In fact, at AWS, I do no research. I'm one of researchers at Dartmouth. But I think maybe a little bit more to that point about kind of what my own journey to get here was. When I graduated my PhD, so my research group was just across the Oxford. And when I graduated, I was one of the last people from my research group to graduate and go into academy and go do a postdoc. And everybody else went into industry immediately. And I think one of the major differences between going to industry versus going to academy is the stability. So as an academic, you can stay at a place for 30, 40 years if you get a position, okay? Maybe not, right? It's just as much a roll of dice in academy at certain levels as it is being in industry where, they might close your division or they might say, all right, we don't need a software writer anymore. We need you now to switch over to, whatever we need to switch to. Or you switch this team in Seattle. Oh no, you're gonna switch this team on the East Coast, and you just move because they're paying you a lot of money to do it. So there's also the money difference. It's not nothing to scoff at, but the freedom of the money, even in industry, it can become very quickly not free. Because I'll tell you immediately, don't do what you want anymore. You need to do this thing for this customer. And so that happens much more than it would have maybe 20, 30 years ago when Bell Labs was sitting around and taking a penny off for every phone call. And then they just give them money to do whatever they want. Now it's more like you need to do this thing, you need to build this device, and that's it. So.
Hi, I'm an incoming PhD student at UMass Amherst, Dejan James. I wanted to ask a little bit more about Amazon Braket and just kind of like relating it to big data. I know that Amazon itself is a big kind of proponent of big data. So I wanted to know that even though that it's more customer focused, does like Amazon Web Services or just Amazon as a whole, do they have any kind of intention of using these services for managing their own types of data and their own information that they're generating?
Oh, that's an interesting question. I guess maybe to tell you a little bit how AWS runs is more like an octopus than a monolith. And so if somebody from some other division of AWS said, hey, we want to use quantum computing for it, they treat them like a customer, maybe an internal customer, but it would still be speccing out what they need to do. How do we help them? What do you want? And then you'd be in the customer pool. Maybe not a customer per se, but what do we need to do to support you? And then you are now our customer too. And so when we say we have a customer demand because the people over in hardware want us to build a quantum spec for them, then it becomes just having another customer inside the portfolio.
So there is that kind of like in-house.
Oh, there's tons of in-house components. I mean, if we need help, so for instance, the Quantum Center for Quantum Networking does a lot of things to think about how do we actually integrate this into other parts of networking. And so they would interface with the networking team. So for instance, security protocols that are post-quantum would be a discussion with both the quantum team and the security team. And so these things end up being sort of like the idea that you can think one's a customer, or maybe they're both combining to help a customer, or maybe we're a customer for someone else who's writing our docs, so on and so to speak. So the whole customer obsession kind of goes very, very deep, that everything's a customer. And there's no such thing as not a customer. So, yeah.
So let's thank James again. Professor Nathalie Deleon is an associate professor of electrical engineering and computer engineering at Princeton University. But her roots are both at Stanford and here. She actually received her BS at Stanford University. I did my graduate work there too. Loved Club Med Palo Alto. And I got her PhD from Harvard. But your PhD from here is in chemistry, right? Yeah, so he's another chemist converted. I say chemist is the best training for everything. But she also stayed here a little bit longer and worked as a postdoctoral scholar under the CEQUEM program, the Center for Integrated Quantum Materials, which Bob was the director for over 10 years. That NSF-funded S&T Center is actually now kind of finishing its run. As I mentioned, she'll talk a little bit about the work ongoing, but like I said, there's a strong effort in driving quantum technologies also at Princeton. She's one of the co-directors of the Co-Design Center for Quantum Advantage, which is a DOE-funded quantum information center. I won't go through all of her awards or I'll waste all of her time, but we're phenomenally just grateful that Nathalie has been able to visit us today, because I actually think she's working on one of the most important problems in this area, solving the material science of qubits. And so I'll cede the floor to Professor Deleon.
All right, thanks, Bill, for the very nice introduction and warm welcome. I actually was at Harvard just a few weeks ago, so it's a little bit funny to come back here. So for those of you familiar faces in the audience, I'm sorry you're hearing some of the same stuff today. But last time I mostly talked about NV centers. Today I'll talk about superconducting qubits. Okay, so this is going to be a much more technical talk, so everyone strap in. So let me just, as a broad introduction to what my group does, because the topic that I'll talk about today is really only about a third of the group. We mostly actually work on color centers and quantum technologies based on diamonds. So about half of the group works on nanoscale quantum sensing with nitrogen vacancy centers in diamond. We've sort of mostly been working on condensed matter physics with those tools over the last couple of years. We also have an effort on integrated nanophotonics and solid state defects for quantum networks. We've recently had a little bit of a renaissance in doing nanofabrication in single crystal diamond, and I've started a new effort over at the Princeton Plasma Physics Lab where we're now growing quantum grade single crystal diamond at scale. And then kind of this last third of my group, this effort has only turned on in the last 4 or 5 years, is taking some of the material science and surface science tools that we understood from Diamond World and applying it to superconducting qubits to try to solve problems there. Okay, I don't want to derail my own talk too much, but at the end of James's talk, this gentleman in the front asked, how big of a system do you need? Which is a very good question. So let me reframe the question a tiny bit. Superconducting qubits are this very successful qubit platform. This is now the basis of a lot of the large-scale industrial efforts. This is IBM's processor, Google's processor, the core technology that AWS in Pasadena is working on. And people are now kind of making these devices that have tens to hundreds of qubits, which is a really impressive engineering feat. And as James alluded to, there has been a lot of really beautiful science out of this. So people are now starting to explore executing quantum chemistry algorithms, simulations of different Hamiltonians, studying many-body physics, and like a lot of Nature papers is sort of the status of the field. And then very recently, just in the last year or two, there are now all of a sudden experimental demonstrations of quantum error correction, which is just incredible, because I think if you had asked anybody in the field 5 years ago, 6 years ago, let me turn it around a little bit, because I know that we have a lot of young scientists here. If I had applied for a job 6 years ago and said, I'm going to work on fault-tolerant quantum computing, I would have been laughed out of the room, right? So people would have said, no one's going to build it, it's way far away, it's science fiction. And now we're living in a world where suddenly there are logical qubits. There are logical qubits in neutral atoms, in trapped ions, and superconducting qubits. So maybe it's some lesson about not listening too much to your elders, because everyone would have been correlated wrong very, very short time ago. So this is really interesting. So, one question is like, how big of a system do you need and how good of a system you need? And I think quantum error correction is one of the real near-term goals. So correcting errors in a quantum computer is fundamentally more difficult than in a classical computer and requires a lot of qubit operations and a lot of qubits. So all of the systems that we have now are still below what you would call break even, which means that if I do all of the operations that I need to do to try to keep this information alive, I actually do worse than if I just used my single qubit to begin with. So in some sense, what we're trying to reach is a phase transition in our capabilities, because once you can actually do these operations with high enough fidelity that you can keep information alive longer than if you did nothing, you have a fundamentally different system. Okay, so all of this progress hides the fact that, one, we're not that close to being able to build these fault-tolerant systems. And second, inside of superconducting qubits in particular, there was sort of this shameful fact that single qubit coherence had not really improved for about 10 years when we entered this field. So you can make a plot in analogy to Moore's law, where you plot single qubit coherence or lifetime as a function of year. And there is this really impressive sort of march of progress from the invention of the first Cooper pair boxes by Yasu Nakamura and John Clark in the late 90s, all the way up to transmons, which were invented by Rob Schoelkopf, and then improved upon also in Rob Schoelkopf's group at Yale. And they got up to around 100 microseconds. And 100 microseconds is around where everybody is stuck. So this is the IBM systems, the Google systems are all also roughly here. You can go and look up these qubit parameters yourself. You just log into Qiskit, and this is roughly the distribution that you get. Okay, so the last time that people set a record before our work was about 2012. 10 years is a long time for there to be no progress, and there are obviously lots and lots of groups working on this, billions of dollars being spent, literally thousands of scientists working on it. Okay, this appears to be limited by dielectric loss, and there were a few things that the community already knew about where this loss was coming from. So the first is that the loss appears to be related to surfaces and interfaces. So if I plot the quality factor of a resonator, so like how long an excitation can live, as a function of the size of the device, you can see that in general, as they get bigger, they get better. And if I look at the sort of bulk constituents of the material, superconductors obviously should be dissipationless, and I can just ask, where is all the dielectric loss coming from? And I look at all of the different materials. If you measure those at room temperature with high powers, you get quality factors of something like 1 billion. And people were at a quality factor of more like 1 million. So we have 3 or maybe even 4 or 5 orders of magnitude to be able to recoup here. The other kind of weird fact about losses in superconducting circuits is that they get worse at low temperatures and low microwave power, which is the parameter space that you need to be in to do qubit operations. You have to put in, on average, 1 photon at a time, and you have to go down to millikelvin temperatures. So this is a plot of the loss tangent, so higher is worse. And as I turn the temperature down below hundreds of millikelvin, you see that it blows up. And then also, if I turn up the microwave photon power, I can make this loss kind of go away. So this is fundamentally weird, because if I gave you a crystal of something and I said, how lossy is this thing at green wavelengths or something like that, you'd shine a laser at it, you would look at the attenuation on the other side, you'd do a Beer's law calculation, and you wouldn't really sweat the power of the laser too much, right? If it fluctuates by a factor of a few, you're still gonna get the same number at the end of the day. So here, what this says is that the losses, the number that I would get actually depends a lot on the power of the laser. And all of these things sort of point to, I have something that can saturate. So I have something that causes loss that if I drive it hard enough, I make that loss go away. And this is why in this literature, you hear a lot of people talk about so-called two-level systems, because two-level systems are things that intrinsically saturate by definition. All right, so we're looking at for things at surfaces and interfaces and things that could be like two-level systems. And I can just stare at one of these devices and say, okay, there's a boatload of interfaces and surfaces here. Maybe I can figure out which surfaces are actually responsible for the loss and come up with a playbook for systematically, characterizing and categorizing this loss. So let me just take one step back and give you a cautionary tale from Diamond World, because I think this really informed my particular scientific approach to this problem. So sorry to give you like a second introduction in under 3 minutes, but most of my group, about 2/3 of my group, is actually working on this little color center in diamond. So if I take a diamond, punch out 2 carbon atoms, and stick in a nitrogen, I get something called a nitrogen vacancy center. This gives me a very deep electronic defect that even has excited states, electronic orbital excited states that are also deep defects. So I can do things like put in photons, take out photons without really thinking about the surrounding diamond lattice. And you don't need to know very much about this, particularly for this talk, but the key thing is that it has very long quantum coherence times, even at room temperature. So there are a very large number of groups all around the world, including several at Harvard, that are working on using this as a quantum sensor. And one of the images that we always put in our grant proposals is you have an NV center, it's under a diamond surface, and you put it within nanometer distances of, say, a protein, and then you can use this thing to do nanoscale magnetic resonance imaging. Sounds like very cool and sexy, but nobody can do it. And the reason that nobody can do it is because these really long coherence times that you have are really only true in the deep bulk of high purity diamond. And in order to do something like this nano MRI experiment, I have to bring this NV center really close to the surface of diamond. And what we see is that the coherence times get much worse as I come close to the surface. Okay, so everyone sees this problem. You have this horrible power law scaling. So instead of my milliseconds of coherence, when I get within a few nanometers, I have more like hundreds of nanoseconds of coherence, which is really bad. So if you had asked anybody in 2011, maybe, or something like that, what is the cause of this noise at the surface that screws up my NV centers, they all would have given you the exact same answer, which is that, oh, I can do a measurement of this noise. It's very, very easy. If I do a Hahn echo coherence measurement on my NV centers and then use another microwave tone to probe what else is in the bath, then I can see a little signature of these spin 1/2 G=2 electronic spin defects at the surface that are probably things like dangling bonds or something like that. This is a double electron-electron resonance measurement, so people call these deer spins. And we can see them, and they're ubiquitous. Because I can see them, this must be the problem. And you can do things like take a lot of data where you look at different NV centers and you plot, for example, the Dirac coupling versus the coherence time. And this looks like a pretty darn good correlation, right? So this looks like a little bit of a smoking gun, that as the Dirac coupling goes up, my T2s go down. And similarly, as my T2s go up, my Dirac coupling goes down. However, and I think I sort of gave away the punchline with the title of my slide because I'm lazy about animations. What we discovered is that the surface spin, this apparent correlation is actually a red herring. The apparent correlation is a correlation of both the Dirac spin coupling and the coherence time with depth. And in particular, we could make surface conditions where we could scramble these coherence times and Dirac spins with respect to one another. So the analogy here is it's like you're in a parking lot at nighttime and there's a drunk guy looking for his keys, and then the only place that he's looking is right under the street lamp because it's the only place where there's light. The probability that his keys are there is extremely small, right? But it's just the only place he can look. And I think there's sort of a deep analogy to a lot of the work that people have done in trying to do material science for superconducting qubits here as well. Okay, so in the end, what we did was instead of just focusing on these Dirac spins, we did a lot of direct material spectroscopy of the surface. And then what that allowed us to do was come up with a very large number of other sources of noise. And we used that for directed kind of improvements, and we were able to get about an order of magnitude increase for a shallow NV coherence. Okay, so that's the background. So now let me take this grumpy surface science perspective and apply it to superconducting qubits. So we started thinking about this problem, I guess it was like 2019. And basically, I had sat through enough of these talks, hearing people talk about two-level system losses and superconducting qubits and seeing this horrible Sholkov's law plot and saying, like, I bet they're missing something big. So Bob Kava, who is a solid-state chemist, who is most widely known for having made some of the first high-TC superconductors based on cuprates when he was at Bell Labs, and more recently doing single crystal synthesis of topological materials. The two of us started talking, and then we roped in Andrew Hauck, who was one of the inventors of the transmon and has this big superconducting qubit lab at Princeton, and with whom I talk all the time. He's right down the hall. And we said, Andrew, what is the material system that you guys are actually using, and what do you know about it? So the Hauck lab qubits at the time were mostly made out of niobium. They have an aluminum oxide junction to form the Josephson junction in the middle. And then the whole thing is sitting on sapphire. This is essentially the IBM material stack too, but they work on silicon instead. And we immediately came up with two hypotheses for where this loss might be coming from. My bias from Diamond Land is that it's probably just covered in junk. You just have hydrocarbons everywhere. And if you haven't done a good job of cleaning your device, if you haven't thought about it, it's definitely covered in junk. And if I take the loss tangent of stuff, like if I just look up anything in a handbook, I get roughly 10 to the minus 3. The surface participation ratios are also 10 to the minus 3. 10 to the minus 3 times 10 to the minus 3 is 10 to the minus 6. That's my Q of a million. So if nobody has thought about this, that's probably their limiting factor. Bob pointed out there was another problem with this material stack, which is that he said, why on earth are you using niobium? That is the worst possible material to get a handle of, because I spent a bunch of time in the 80s. This is me as Bob, by the way. In the 80s, I was a child. In the 80s, studying the oxides of niobium. And basically, if you look at niobium different, you get a totally different composition of oxides. Some of these things are semi-metals. Some of them are different kinds of insulators. So this seems like it's just impossible to ever get control of. So we basically did two things. One is we came up with a bunch of ways to clean the devices and make them contamination-free. And again, a lot of this is just looking at what you've made to make sure that you actually don't have any contaminants. And then the other is that you need to find a material that doesn't have these really complicated oxides and is pretty robust to processing. And if I clean it, it will still look okay. So we just went one down on the periodic table to tantalum, which is a superconductor with a critical temperature of something like 4 Kelvin. We can deposit it epitaxially on silicon or on sapphire. And as advertised, it actually does have a very well-behaved oxide. So you always get the same stoichiometry. It's a little bit like aluminum cans never rust because they have a self-limiting oxide. Similarly, tantalum has a self-limiting oxide. So almost no matter what you do, you just have 2 to 3 nanometers tantalum 205. And also, as advertised, it's an extremely robust material. So we can do things like, this is the carbon 1s peak in XPS. So it's sort of a reporter on how much hydrocarbons you have on the surface. And we can dip it in sulfuric acid and peroxide. We can boil it in perchloric, nitric, and sulfuric acid and do all of these crazy things to it. And the carbon 1s goes away, but the Ta205 always looks basically the same. And the punchline of this activity, so there was also a very large nanofabrication story on the back end, figuring out how to handle these materials, but we were able to sort of immediately get to qubit lifetimes exceeding 300 microseconds, which was a jump of about a factor of 3 or 4 over the state of the art. So we got to add our little, improvement onto Sholkov's law plot here. So this was, a nice big delta because we did one pretty simple materials science, study, and we're able to improve on the global state of the art by a very large margin. And since our work, this has been reproduced in many labs. So there was a group in China that was able to get to T1s of 0.5 millisecond. There's a group in Belgium at IMEC that has also developed tantalum on silicon, where they're able to get to these Qs of a few million. And Michel Deveray's group at Yale took a tantalum qubit and integrated it into the GKP code to realize the first sort of break-even quantum error correction. So tantalum was one of 3 or 4 improvements to make that happen. Okay, so that was a few years ago. So since then, what we've been mostly focused on is now trying to systematically understand, well, what are our losses now? So we have, world state-of-the-art devices. So how can we get rid of, but we're still not at a fault-tolerant system. So how can we do even better? So what we've been doing are systematic studies of tantalum resonators. This was work led by Kevin Crowley in Andrew Hauk's group and Russell McClellan and Avik Dutta in my group. And the idea is that we really simplify the measurement. So instead of just making a qubit where we have all of these different materials at play, we just have sort of one metal and one dielectric. And we can interrogate this over a very large range of parameter space to now try to use physics modeling to understand where our losses are coming from. So if I just look at transmission through these resonators, what I'll see is a little dip that comes from the resonance frequency. And then sort of, as a lot of people have seen, as we turn up the microwave power, the quality factors go up. So we see this behavior that's consistent with these saturable 2-level systems. And for any experts in the audience, I'll just point out that I believe we have the record high power quality factors. It's not really relevant for qubits, but the reason that it's really important for us, so we can get up to, this is actually an outdated number, but about 500 million. And the reason that this is really important is if you're trying to see extremely subtle sources of loss, this is now sort of a ceiling. So it's important to get this number very high so that we can see lots of different things. Okay, and then we did something that for some reason people weren't doing in the community, but is a very powerful approach for really understanding microscopically where the losses are coming from, which is that we took these power dependence curves and then we just changed the temperature and then took a power dependence curve at many different temperatures. And the idea is that you get this whole family of curves, and there's a lot of wiggles and wobbles here. But what I'm going to assert is, okay, I can write down a model for what this quality factor should look like as a function of temperature and power. And there are some mechanisms that are temperature and power dependent. There are some mechanisms that are not power dependent, but only temperature dependent. And then there are other mechanisms that are temperature and power independent. So I can now sort of sort everything into being dependent on these 2 different parameters. So this is 2-level systems can thermally saturate and then also saturate with power. These are quasi-particle losses that turn on when you break Cooper pairs in the superconductor, and then now you have these free electrons around that give you resistive loss. And then I have something that sets a ceiling. Okay, so we don't have to talk about the details of this model, but the key thing is, the real takeaway that I want you to have is this is a very beautiful fit to the data. So by just writing down something with 7 free parameters, I can really capture every single bit of curvature for these things right away. And there's maybe like a little bit of an under the hood multidisciplinary story here too. A lot of this data fitting that we use now is really inspired by the kinds of techniques that people use in data science, which is different from how I think physicists normally approach this problem. So the typical physicist strategy, and this might be outdated now, is that you would sort of lovingly fit this one curve by, by using your intuition and things to constrain your fit. And then you would use that to cross-constrain these other curves, and then you would keep on doing this iterative fitting until you got something that looked nice. Looking nice is not a very good statistical test. And what we all kind of asked ourselves when we went home for, this was my COVID project. I was stuck at home for COVID. I said, the data scientists have like all this multi-parameter estimation. They must have something more sophisticated that you can do. So the key is we fit the entire data set simultaneously, right? So instead of one curve at a time, it's really the entire data set. It all has to come from the same model. And then we can use statistical tests of goodness of fit. And that's how we're able to get such tight constraints on all of these parameters. Okay, so now the key thing here is that one of these free parameters, this prefactor on the 2-level system loss, this now looks a lot like a materials parameter, because this little prefactor is basically the linear absorption due to 2-level systems. So this is very intriguing because one of the real pain points in this field is how do I compare apples to apples? If I do a measurement And I cool down my qubit and I say I can get a T1 of 400 microseconds. And then, Rob Cholkoff tries to do the exact same thing at Yale, and he cools it down, and he's like, "You're a liar. I only see T1 of 100 microseconds." And then we discover, as we, swap packages, that we do our filtering slightly different, and we do our Christmas wrapping and our magnetic shielding slightly different. And it turns out that we're always looking at this horrible composite parameter that, that says I have to do literally the exact same experiment, the exact same fridge, the exact same wiring to be able to reproduce what's happening in somebody else's lab, which is a terrible way to do science, because now there's no way for us to rapidly figure out what is actually going on and how do we actually compare different material systems. So what this allows us to do is it says, okay, let's say I've really screwed up my packaging, and now I have some radiative loss. Then what I know is that that is not going to have any power or temperature dependence, so that will show up as all these curves are a little bit squished. But I can still independently fit all the curvature and get out this two-level system component. Okay, so the key playbook here is you come up with a measurement strategy that gives you access to a material parameter. And then what we can do is take that material parameter and do things like make different geometry devices. So as we make these things bigger, we can change the surface participation. And what we see is that as advertised, as we make the devices bigger, so this is to 0th order sort of like the pitch between these devices, the Qs go up. And this is, again, this isn't just Q, this is the linear absorption due to two-level systems. So we decrease the two-level system component as we get them bigger. But then maybe they're starting to kind of saturate at the biggest devices, so we don't keep on increasing. And then I can do things a little bit more sophisticated, which is now start to do different kind of surface conditions. So I can dip it in acid, try to oxidize the surface and do lots of surface conditions. And what I find is that all of this data fits best to, I have some surface-related two-level system loss, but I also have a bulk related two-level system loss that has to come from the underlying sapphire. Okay, and this kind of full data set maybe also shows the real pitfall of just doing these single qubit measurements and then trying to compare from lab to lab, because somebody could make their qubit out here or out here and we'd get very different measurements, and we'd even be probing completely different two-level system baths. All right, so I'm going to skip over the detailed modeling, but let me just say one of the puzzles that sort of fell out of this is that we were trying to do things like increase the surface. So the natural surface loss is the surface oxide. And we were trying to do things like increase the surface oxide to increase the loss. And what we found was that the surface oxide loss, or sorry, the surface loss was not extensive in the surface oxide thickness. So sort of your most naive guess was wrong here. So then we turned to much more detailed materials characterization of the surface oxide. So this was all in collaboration with Brookhaven National Lab and led by Russell McClellan in my group. But what we did was X-ray photoelectron spectroscopy. So you send in an X-ray, you kick out an electron, and then you use that to look at sort of the chemical environment of the electron that came out. And then because it's at a synchrotron at Brookhaven National Lab, what we're able to do is also change this X-ray energy. And then that changes sort of the sampling depth, because as you go to higher energies, you're more likely to be able to see an electron from deeper away from the surface. So let me just say, full disclosure, I normally hate XPS because as a materials characterization technique, because normally what you're doing is, so this is the tantalum 4F spectrum, and I have, these two peaks here and these two peaks here. These are the tantalum metal, these are tantalum oxide. And then I have this big mess down here. And then if you go into the XPS literature, what people are doing is making very strong claims based on, a pedestal where they're putting in 2 peaks or 3 peaks or 4 peaks. And it's, how do you know? How do I know that this is the right number of peaks? You're really just fitting a bunch of structure to something that has no structure. Okay, rant over. So I'm now a little bit of a convert. And the key thing is that, again, there's sort of a weird data science flavor here. Because I'm taking all of these different energy shots, and this is 3 of like 20 something that we did, and all of them come from the exact same material stack, what I can do is, again, simultaneously fit the entire data set. And what I know is that all of them had to be looking at the same oxide stack. So I know now from a statistical standpoint, this is the correct number of peaks. If I add a peak, my chi-squared blows up. if I subtract a peak, my chi-square blows up, right? So basically by using these data science tools, we're able to get access to more information than you would have if you just sort of naively fit the data. Okay, so we use this to try to develop a depth profile of all of these different species. As sort of you would expect, as you go up in energy, the tantalum oxide peak goes down, the tantalum metal peak goes up because the oxide is sitting at the surface. And then we have all of these different stoichiometries that sort of increase and then decrease. So that means that they're sitting at some intermediate range. And then what we're able to do is now build up these profiles of these different surface conditions and then come up with new hypotheses for what might be the microscopic origin of these two-level systems. And interestingly, one of the things that falls out of this analysis is it might be only one of these suboxides, not all of them. So we have to do more to actually chase this down. Okay, so just to summarize this kind of all the published work, the current losses in state-of-the-art devices look roughly like this. So we have some surface two-level system loss, some bulk two-level system loss, and we believe that these surface losses could be related to the surface oxide. They could also be related to the sapphire air interface because that's kind of the remaining other surface that we haven't really tackled. And then this bulk loss, which again is two-level system loss, has to come from defects inside the sapphire. So now there's a whole project of trying to understand what's going on in the sapphire. I didn't show you any evidence today, but we also have some evidence that the Josephson junctions, which are made out of aluminum oxide, also have a loss contribution that is something like this. So in some ways, this is this is very exciting because we can actually see where all these things are. It's also really, really sad because it means that if we kill one of these losses entirely, we've only increased our Qs by like a factor of 50%. So we have to solve all three problems simultaneously in order to push the state of the art. Something about the best patient is one that never dies but is sick all the time. Okay, and then again, our packaging losses are way up here. So we're very confident that we're looking at, really these materials related losses. Okay, so let me just give you, one quick takeaway before I get into the unpublished stuff. So maybe the biggest takeaway is that we saw a really big leap in performance with just trying one more superconductor. So the whole community charitably had looked at like five superconducting films. And then we're stuck at the state of the art because they were really trying to, hit the problem with the only hammer that they knew, which was microwave design. And I think just by trying something, we were able to get this big delta in the state of the art. So it's probably time for people to do a much broader search. And I can write down like 20 or 30 superconducting metal films, varying composition that are easy to deposit and fabricate. So it is worth the big search now that we have a good playbook for understanding the materials losses. The other kind of big takeaway is, and this was maybe a little bit of a surprise and also a little bit of an uncomfortable interdisciplinary thing, but what we found is that material resilience is actually as important and maybe even more important than the underlying material properties. This is a very uncomfortable space for both physicists and material scientists. I think what material scientists would usually like you to do is just say, here are all the properties that I need, deliver me a film that gives me those properties. But this is now a totally different desiderata. This is, I need a film with these properties and I'm gonna dip it in acid and do terrible things to it. And I want you to leave open this big parameter space for me to be able to anneal it and stick it in plasma and do all of this other stuff. And now, this is a very different kind of design space for these materials. Okay, so let me just show you, because I think it's always important to show new stuff, some of the things that we've been working on. So we want to get rid of the surface oxide. A natural strategy to try is to just not have a surface oxide. And one of the things that, the metals that do not form surface oxide are the noble metals. So think gold, palladium, platinum. The problem is that none of those things superconduct. But one thing that I can do is put a very thin film of gold on top of the tantalum before I break vacuum and form an oxide, and suppress the oxide formation. Now, normally if I just spray a normal metal on top of my superconductor, that's a horrible idea because I've introduced a bunch of losses. But if I do a good enough job at making this hetero interface, I can rely on something called the proximity effect, where Cooper pairs can just sort of exist in the normal metal, and the whole thing still acts like a superconductor. So the game here is you want the noble metal layer to be thick enough that you don't form an oxide, but thin enough that you still have full proximatization. So if we put down a little bit of gold, we find that indeed we can get rid of these oxide peaks entirely with just a few nanometers of gold, which is a little bit of a surprise for me. And then if we use these resonator measurements to extract what the effective critical temperature is, we see that at this 4 nanometers, we only see a very small suppression in TC. And we can even see superconductivity out to 100 nanometers of gold on 200 nanometers of tantalum, which is really remarkable. And this is all led by Ray Chang and Nana Shumia in my group. This is maybe a little bit too deep. Yeah, I'll talk about it. Okay, so we've done an extremely deep dive in tantalum. And we had this kind of longstanding puzzle in the group, which was that we could deposit films that looked identical when we did DC transport and we looked at X-ray diffraction to characterize their crystallinity. But then when we did this power and temperature dependent loss measurement at microwave frequencies, they had very different behavior. And in particular, these films look like they have this exponentially dependent on temperature loss that turns on at extremely low temperatures. And we couldn't really figure out what was going on. Faranak Brahmi, who's a postdoc in my lab, was not satisfied that this was an outstanding puzzle. So she said, you know what, I'm going to do more materials characterization because I think you guys are screwing up. And what she found was that, the fact that we see the same TC in DC transport sort of hid the fact that there were actually some subtle differences in transport. So if I look at the residual resistivity of the film, so what the resistivity looks like at low temperature right before the superconducting critical transition compared to room temperature, you actually had sort of a clumping of everything that looked like it had this exponential loss, and everything that looked good had a lower RRR. We also could see a different critical field if we did magnetoresistivity measurements. And then if you did a really careful job of your XRD and calibrated it properly, we could actually see a shift between these two different populations of something like, half an angstrom. 0.16 angstroms. And okay, so there were clearly differences, and there's sort of a hint already in all of this data about what the differences are. So these XRD peaks look a lot messier and kind of broader. So the good films have more disorder. Again, a weird thing for material scientists. So just to summarize, what we find is that the films with this kind of bad AC loss behavior are actually the cleaner films. So these are in the clean limit. And then the films that look like they have a nice high TC are in the dirty limit. So the story here is, we were trying to get rid of two-level systems. We tried to make these films as good as possible, made single crystal, extremely low defect density, all of that stuff. And we accidentally induced a new source of loss. So a natural hypothesis now is that these are vortices. So if I have superconducting vortices that throw through my film, if you make a really, really nice film, there's nothing to pin these things so they can move around and also give me losses. Okay, so it looks like we can pin the vortices with disorder in the material. We can also do things like just explicitly pin them by doing fabrication. So now this is a film that started out like one of these low activation energy, vortex loss films. And all we did is take it and drilled holes all over the place. And we were able to convert it into a high TC film. Okay. All right, so this is a very detailed story, but I think the detailed story for anyone who wants to work on tantalum is that this, if you make things, this disorder can be introduced either via film growth or by fabrication. The differences in the films are actually pretty subtle. But maybe the broader message for material scientists is that better is not always better. This was a case where we tried to make the most perfect films we could, and then we ended up with worse device behavior at the end. All right, I feel bad doing this, but I had to take off all of the identifying data when I discovered that this was going to be posted online. So I will just tease, because we're filing for patents and stuff. So I'll just tease that we have been able to push the state of the art by another factor of 2. So this work is led by Matthew Bland. All of the data that I showed you earlier is bounded by this blue line and this gray line here. And because we're able to say, We know we have surface losses. We know we have bulk losses. We've just tackled them both at the same time. And we've been able to now push our surface losses up by a factor of 2 and our bulk losses up by about a factor of 3. Okay, so forthcoming. All right, so let me just acknowledge the whole group. It's now a pretty large team working on this, new materials for superconducting qubits. All of the work is in very close collaboration with Andrew Houck and Bob Kava. And by close collaboration, I mean true collaboration. Our students get up and work on the same fridge together, and it's just one, really awesome super team. So it's just been really, really fun. The people doing the work that I talked about today we now have a very large number of alumni from the group. So Russell McClellan, Avik Dutta, Leela Rogers, Alex Place, and Jin Kui, and then Huang Li, Yuchi Gang, and Trisha Madhavan, who are all now at Harvard. And 2 of them are here. And then the current team is Ray Chang, Nana Shumia, Apoorv Jindal, Kevin Crowley, Alex Pakpor, Faranath Brahmi, Matthew Bland, Atarva Joshi, and Izzy Hedrick. And then I promised that I would do some advertising at the very end. So as Bill mentioned, Princeton has the 3rd quantum science and engineering PhD program in the world. We are very excited about it. We launched it last year, and we accepted our first incoming class of 11 people who will be showing up in August, September. So of course, we will be accepting applications for that program again at the end of this year. The idea is that we have a very strong cohort formation that really takes a core set of courses in quantum information, quantum technologies, and quantum mechanics. And then you go off and do, whatever other courses you want. We also have a postdoctoral fellowship program out of the Princeton Quantum Initiative. I'm not sure about this date because we haven't posted it yet, but it's generally sometime in October. And there's a very, very broad community of people at Princeton who are working on quantum with this shared language of quantum information science. So it's a really exciting time to come to Princeton. The university is making really large-scale investments in quantum. And we have a new building that should be online in a few years. So please come visit us. Please stay friends. Please apply to these things. And I'm happy to answer any questions.
Hello again. I'm James. My question was related to the defects you see in the diamonds that you make, where you have like those nitrogen gaps. Have you tested just switching one or a few atoms in that small crystal lattice with things that aren't just carbon or some other metal, and seeing how it affects the deficit in that energy gap you see?
Yeah, so there's a large, so that's like one of the little slivers of things that I didn't talk about. That there's a large community of people who are trying to look for new defects in diamond, where instead of a nitrogen next to a vacancy, you put in some different atom, or you put in different clusters of atoms. The work that James talked about out of Harvard, where they do this quantum network remote entanglement stuff, that's all based on silicon vacancy centers in diamonds. So stoichiometrically the same as an NV center, but instead of a nitrogen, you use silicon. So there's a very big community, and I think there is still sort of this outstanding goal of, no one has like a very good quantum memory for quantum networks. So it would be great if somebody could come up with one, but the best in class are all, color centers in diamond or other dielectrics. So there is a big outstanding challenge there.
Hello, my name is Malcolm. I'm a rising sophomore at Howard, and I attended your and Dr. Houck's talks at Circuit QED at 20 at Yale.
Oh, okay.
But
so
I guess
you saw a lot of this already.
Yeah, I also like a lot of the 2-level system talks, and then I was like, when I got to your and his work, I was especially like interested. I guess going back to the work that you're doing with the tantalum. I talked with Faranath between one of the days in terms of her work with the XRD, but would you be willing to go back to?
Yeah.
That's. I guess my question in general is, what was the classifier that she used to go into a deeper study of the magnetoresistivity?
You mean like how are we color coding these things?
Yes.
Yeah, so it's based on these resonator measurements. Mm-hmm. So when we do this power and temperature dependence, in general, when these things start to kind of come together and drop exponentially, one of the ways that you get that is with quasi-particles. So you just break Cooper pairs and you make quasi-particles, and then those give you resistive loss. So in some sense, it's a measurement of the critical temperature of the superconductor. And that's how we were interpreting it, which is why these are all labeled as high TC, low TC, or whatever. It turns out you can get the same behavior with vortices dragging around. But the key thing is, where do you start to see the onset of this exponential loss?
Thank you.
Hi, thank you for the talk. So working at Brookhaven, I know that there's a huge focus on niobium for SRF cavities. And I was wondering, with all the work that you've been doing with tantalum, is there any interest or initiative at scaling up because of the properties that your group has discovered in terms of like doing things with SRF? I know that BNL has a lot of interest in that for future colliders or accelerator science.
Yeah. So actually, one of the National Quantum Initiative centers, the one that is based out of Fermilab, SQMS, a big kind of thrust is trying to take these SRF cavities and then try different materials and figure out the surfaces. And they've already done, based on our work and based on the NQI, have tried encapsulating niobium with tantalum. I think they have some new results that they haven't talked about publicly yet, where they're making it completely out of tantalum. So yeah, there is a lot of activity in this. Personally, I think there's also probably an opportunity taking another look at things like detectors. So for example, if I think about like kinetic inductance detectors, a lot of the game there is high power queues, not low power queues. So it's a different parameter space from qubits. But we now have the best high power queues in the world by about an order of magnitude, and then compared to the actual literature with detectors, like 2 orders of magnitude. So it's sort of worth now taking another look at some of these other systems, like maybe we have a broader axion search if we can make like better arrays of tantalum resonators.
Thank you so much.
Hello. Thank you for a deeply disturbing talk. So I had a question, right? So, there are all these efforts like MGI, et cetera, to try to search for new materials. And here you mentioned...
What's MGI?
Oh, sorry, Materials Genome Initiative,
yes,
when
right.
people are trying to do these like DFT-based searches.
Mm-hmm.
But what you're finding, right, is that a lot of this physics is dominated by defects and surfaces, which are, I understand, painful for the theorist to calculate. So do you have any thoughts on, you say, okay, you have these 20 candidates, right? And this took, I don't know how long to do for even just the tantalum work or to figure out these problems with niobium. So how do you actually search these, say, 20 systems or, later on, thousands of systems to go and say, yeah, this could be a good candidate?
Yeah.
Because I wouldn't have guessed, like say tantalum with 3+. That's just weird.
Yeah. So, okay, there's like, gosh, how long do you guys have? So I guess first let me say, it took us a long time to do tantalum, and it took us a long time to come up with this playbook. But now that we have this playbook, we can go super fast. So we're doing like a new binary metal system every month. And we can try like 7 of them at the same time, right? So part of it was really just figuring out a way to actually do the materials discovery at all, which people had not done in the past. And I think in particular, the way that certainly in superconducting qubit land, and I would say much more broadly in all quantum, all the qubit stuff, people were not doing systematic material science and were not doing even systematic physics. They were largely just doing A/B testing. Like, I have this guy and I have this guy and I cool them both down and this one's better than this. And that's the slowest. It is the least amount of information per unit time. And you're always looking at these very convolved factors, and you might get the wrong answer a lot of the time. You have no way of knowing it. And that process was never going to converge. So you don't have an actual literal soapbox, but if you had one, I'd stand on it and say, what we need is a new kind of material science, and a lot of the same physics that we already had, just people weren't using it. They weren't using all the tools of physics that they had available. They were just using their qubit measurements.
All right, thanks.
Actually, do the mark and then you, and then I think we're going to end it with that.
Thank you very much for the presentation. The question I have is regarding the quality factor. It seems that you have extremely large quality factor that is on the order of billion. Now, we know this is the stored energy divided by the dissipated energy. That's what gives you the quality factor. Have you considered any magnetic material or any other material that can help you improve the stored energy in such device as far as your experiment?
Yeah, so it's hard to beat a superconductor because superconductors have no dissipation. And the only reason that we have dissipation here is because they're also inductive, which means that you inherit the dissipation from the surrounding materials. So the best possible thing would be just a metal superconductor floating in vacuum. Unfortunately, we can't do that because you got to do fabrication and stuff. But my intuition is that any other kind, it's the only thing that's dissipation free. So any other kind of phase that you tried to put excitations in, you would not be able to do better than this.
Hello? Okay. So my question is, could you possibly elaborate on the solid state and the photonic part of what your lab is doing, especially as it pertains to the material science side of it? Particularly, I'm interested in either silicon carbide or other combinations of metals where it would be possible to establish, like you said, one of those quantum memories that we're kind of aching for. It seems that no matter how much progress we made, we always stumble onto the material side. And it seems like you've developed a pretty good formula of studying materials, not necessarily the result you wanted, of course, but that the recipe to do it is in such a way that it could potentially inspire other scientists to follow along your path and discover these same materials alongside the way you were doing it.
Yeah, maybe we can talk offline about the photonics and quantum network stuff because it's a little off topic here. But maybe I sort of I'm not sure what the right word is, cringe a little bit at the materials scientist characterization because I'm not trained as a material scientist at all. And I think the material scientists would disown me. they do not claim me. And the way that I see it is it's not that I came into this saying we need to use material science to solve these problems. The way that I see it is we have a thing that we are aiming at. What does it take, right? And sometimes the answer is physics, but sometimes the answer is chemistry. And sometimes the answer is data science. And sometimes the answer is machine learning. Some of what we're working on now on the quantum sensing side with multiplexing is trying to figure out how to handle these giant data sets and how to be able to do optimization in real time. And that has nothing to do with what you're trained for. So I think the key is if what you really want to do is do a thing, you just have to be brave enough to do whatever it takes to do that thing. And most of Mother Nature and technology is not going to come to you. It's not going to craft a problem that's exactly perfect given your training up until this point. So I think that, I know that what I do right now is very material science inflected, but I don't see us as necessarily trying to take the tools of material science and use that as a hammer to solve every problem. I see it more as that is clearly the key pain point for a lot of these systems right now. If we get past it, there's a different pain point. And then maybe my lab is just working on, bump bonding and packaging 20 years from now.
Yeah, at the end of the day, it is an interdisciplinary science. So I think, that's part of it comes with the bargaining of it, right?
Exactly.
So let's thank Natalie again.